Covered in the lab?
Yeah, we could do one.
All right, so I'm going to cover the first one now in lecture. We're going to cover every problem now, today, in an hour. Okay, here we go. We're going to do lab 3 right now together in this lecture. Okay, exercise 1. Detecting prime numbers. Now, when you sit down to work, I recommend that you just do git pull, okay? To get any commentary, any files that Jaren or I have entered into your repository, please remember to do git pull. That will also avoid having a conflict when you try to push your changes. That's another reason. There's 2 reasons to do git pull. All right. Let me copy another program so that we have a starting point. So I don't want to have to type all that in. And I'm just going to do this. This is how I recommend that you start your problems. And we didn't even read the problem. I mean, we know what it's basically about. It's some command line program that will do something. And so I'm going to take that out. This is a minimal file. Oh, that's not open. All right, so we build that, build that, get the executable and run it. Now it says OK. All right, so that's the starting point. Please start at that starting point. Write a console program that asks the user to enter an integer greater than 1. And let's just copy that text right there. We don't have to go any farther. Let's just do that part right there. Enter an integer greater than 1. We could do that. Sorry. But I'm going to just type ahead a little bit here. I'm going to declare an integer n, and I'm going to read in the value that the user enters. So we prompt the user with a sentence, declare an integer n, and then we wait. We wait. Cin greater than n is called a blocking call. The execution of the program halts there. It stops. It waits until the user types something at the console and hits the enter key. Then this statement completes at that time. And n is filled in with the value that the user entered. Now, notice here we're not bothering to check that what the user enters is a valid integer. So that's an issue. That's an input validation problem that we are not covering. Okay, so just to keep that in mind.
If you were to cover it, wouldn't you need to have it throw an exception?
Well, like I said, we're not going to cover it, so it's not a big deal. I mean, it has to be done, but it's kind of it's just messy, necessary, busy work that you need to do with a real program. All right, so here's a number, say 44. There we go. So we have that running. The program determines if the number entered is prime and writes a message to the standard output stream stating whether the number is prime or not. For example, if the user enters 42, the program displays 42 is not prime. If the user enters 47, the program displays 47 is prime. So I'm going to declare a variable called is prime. No, I'm not going to call that. I'm going to do it differently. If n is 42, then we're going to say, I'll say n is not prime. I'm going to put a new line character right there. Else n is prime. We run it. 42. N is not prime. Let's run it again. 47. 47 is prime. Seems to work. Just kidding. So n is 4 is prime. So that's wrong. Okay. We're just getting. Do you see what I'm doing? I'm just sort of shaping up the code. Just playing with it. Just getting part of it to work right. Just so I can see the outline of how the solution is going to crystallize. All right, so we'll need a different test here. Let's do something like this. Let's declare a Boolean variable, and it's going to be found divisor. Found divisor for n. And let's set that to false. And then we're going to look for a divisor. Let me add a K there. And if we find a divisor, then set to true. And then we'll check the value of that Boolean variable. If found divisor for n. We could do this. So if found divisor for n is true, then we're going to print n is not prime. Because if we find a divisor, that means it's not prime. So we're going to start with this variable, found divisor for n. We're going to start by setting that to false, because we didn't find one yet. We're going to look for one. And then we're going to add code in here that does the looking. And if we don't find it, if we don't find a divisor, then found divisor for n remains set to false. That means n is prime. But if we find one, then we're going to change the value of found divisor for n. We're going to change it from false to true. So that when we get to this part of the program at the very end, this is where we print the result. So it's not right. Everything is prime right now.
Why is it saying that 42 is prime?
Huh?
Why is it saying that 42 is prime?
Why is it saying 42 is prime? Because we declared this variable found divisor for n, and we set it to false. We did not change its value. And here we check to see if found divisor for n is true, then we say not prime. But this is not true. It remains false, so we're going to print this. Now, typically you wouldn't see the condition like this. It's extra, it's verbose. It's too many words. This is sufficient because found divisor for n, that variable, is of type bool. So it's true or false. So we can use that directly as sort of the simplest possible expression for this conditional. So this is sufficient. (42) is prime. All right. So now let's look for it. How? We got to look for a divisor. So think about this. Maybe n is 7. So we'll try to divide 2 into 7, 3 into 7, 4 into 7, 5 and 6 into 7. And there's more efficient algorithms, by the way. So we're just going to, just for the sake of learning how to solve the problem in a simple way, but we're not going to investigate the mathematics, much of the mathematics behind it. We're not going to look for more efficient ways of determining primeness, but there are more efficient ways to do this. What we'll do is we'll just try every value less than n, see if it divides into n. If we find one, then we know n is not prime. So let's use a for loop. And we'll use d as our divisor. We'll start at 2. We don't want to try 1. 1 divides into everything. We don't want to hit n, so we want I to be strictly less than n, because n will divide into n. 7 divides into 7, but 7 is prime. So, and then we'll need to increment I. Okay, so that's the for loop. So if n mod I is 0, so if you divide n by I and you get a 0 remainder, then I divides into n. So then we're going to change this state of this variable. Found divisor for n? Yes, we found a divisor for n. (42). 42 is not prime. 47. 47 is prime. You know what? We're going to need a test cases. 2 is not good enough. And in the problem, I asked for 8 test cases. And I want the test cases to be shown inside of a multi-line comment near the top of the source code file. Let's do that. And the purpose of the test cases is to try to break the program. So we'll try 2. This is not. I'll do it like this. Not prime. I'm sorry, that is prime. 2 is prime. And we need 8.
What do you mean by 8? 8 cases? 8 cases?
Huh? What do I mean by 8?
Yeah.
8 numbers. 8 numbers that we'll try.
Oh.
We type in 2, it should say prime. And when we type in 3, it should say prime. When we type in 4, it should say not prime. And let's try, if we type in 8, it should be not prime. We type in 9, should be not prime. (27), not prime. Let me go the other way here. And 42 is not prime. And 47. Now these are numbers don't get these numbers by running the program. Get these numbers because you know that what's a prime and what's not a prime, okay? So let's try all of these numbers. 2, 3, 4, 8, 9, 27, 40. Does anybody else want to try a different number? See, this here, look, this is the smallest prime number. We're not going to try 1. So remember, we prompt the user for an integer greater than 1. We're not doing input validation. If the user types in -1 or 0 or 1, we don't say, oh, sorry, that doesn't qualify. We don't do that. I mean, in a real program, we would need to do that if we had real users. So we're not going to go to that extent. We're going to assume that the user types in a valid integer that's bigger than 1. So the first integer bigger than 1 is 2. That's called a boundary case. See, it's at the very edge. You can't get less than 2. So that's a good number to test. That's a good point. That's a typical place where the program breaks. This is 1 above it. This is the first non-prime value. So that's another place where the program could break. This is, a value that has more than 2 prime factors, 2 times 2 times 2. This has got 2 prime factors, but those factors don't include 2. And in the past, I saw students try to divide the number by 2 and say, oh, it must be prime. It doesn't divide by 2. And no, that just means it's not even. So you make sure you have a test case that is not prime, but is also not divisible by 2. And so I'm just trying to pick numbers that I think I could stress my program, because I want to pass the stress test here. All right, let's run it again, just to make sure I've got it compiled. I'll compile it. All right, 2. 2 is prime. 3 is prime. 4 is not prime. What was the next one? 8? 8 is not prime. 9 is not prime. 27 is not prime. 42 is not prime. 47 is prime. I think I got them all. All right. Is there any questions about this problem? And the thing I want you to focus on mostly is not the solution, but how I got there. Did you see the steps I took? Each little step, I verified. I didn't solve the program. I didn't write the program all at once. That's too hard. You got to break it down into increments. And be very sure that each increment you fully master and understand what you're doing at each incremental step. Run test cases. Make sure it compiles at each increment. Make sure it's producing the output that you think it should produce at that point. Question?
What does bool mean? I'm not sure.
Bool is a data type. Like, there's different kinds of data types. It's a data type that has 2 states, either true or false. The integer, that's another data type. An integer it's either -1, -7, +30, 0. It's an integer value. And it has a range, has a minimum, the smallest number, which is very negative, and then it has the maximum integer. Because, unlike math, where you have the integers are infinite, the set of all integers are infinite, the computer cannot represent, at some point, computer memory, its ability to represent numbers is finite. So it cannot represent, you'll always be able to produce a number that can't be represented by the computer. So, but bool is a very simple data type. It just has 2 states. But an int has 2 to the 32 possible states. I might be off by 1, let's say, okay? I think it's 2 to the 32 possible states. Is that right? I don't think I'm off by 1. But it's close enough. And a double is a different type of data type. It's a floating point number. And internally has an exponent in there. So it's something times 2 to the power whatever. So it can store representations of floating point values. And they're estimates of real numbers. Like, for instance, if you have 1/3, how do you store 1/3 as a single floating point value in the computer? You cannot do it precisely. So you suffer some round off error there. So those are called data types. Is that okay? I know it was a long lecture about that, but that's what bool is in relation to the other data types. That's the point I wanted to make. So that's more than you wanted?
Well, it works.
That works? Okay. The other thing to keep in mind about bool is that in these if statements, and the conditional expression in the for loop or the while loop, those expressions evaluate to true or false. They evaluate to this data type, bool. So that's why we can use a bool variable declared as storing a bool. We can use that directly by itself as an expression, or the if statement condition, or the loop conditions. All right, I gotta keep moving here. All right, listing prime numbers. Write a console program that reads a positive integer entered by the user. You know what? I should change that instruction to a number bigger than 1. The program computes and displays all the prime numbers between 2 and the number entered. I should change that statement to say the same thing here. Write a console program that asks the user to enter an integer greater than 1. So I'm going to change the instructions on this exercise. I mean, this is not bad, but just to be more precise about it. So the user enters in 5, say, and the program prints 2, 3, 5. It prints all of the prime numbers up to the number the user entered. Now, to solve the problem, we need to nest an inner loop within an outer loop. Of course, there are other ways to solve the problem that don't involve nested loops. But I want you to do it with a nested loop because the purpose of this exercise is to learn about nested loops. So I'm going to make a copy. Oh, you know, before I do that, I'm going to push into my repository. All right, that's done. Now I made a copy, and we'll start from the copy. Did I ask for test cases? Develop test cases and include them in a multi-line comment. Let's do that now. Here's the test cases. Here's the input, and here's the output. So if the user enters in a 2, the program produces a 2. If the user enters a 3, the program prints 2 followed by 3. 4, it'll be 2, 3, just 2, 3 like that. And 8, 2, 3, 5, 7 like that. And I'm gonna let's do one more. I didn't ask for 8. Let's do enough to feel confident that we did it right. 2, 3, 5, 7, 11. What's that? I missed one?
17.
17, thank you. Next one? 19,
23.
23.
29.
Nope. That's it, right? Is that it? 23?
Yeah.
26? Yeah, that's it. So those are our test cases. And enter an integer greater than 1. And there's our starting point right there. All I did was modify the comment. Well, this doesn't do anything, it just compiles. So here we have we're going to enter in a number. I'm going to change this number to k. This is what the user enters in. Okay? User enters in a number k. And then I want to try every number from 2 to k. So that's a for loop. So I'll say integer n equals 2. N is less than or equal to k. And if you just did strictly less than k, that's all right, because I don't think I was clear about whether to include k or not. There's our loop, see? We want to try every value for n, because we already have code that checks to see if n is prime, right? So we're just going to embed that existing code inside this outer loop, or we use, rather than getting n from the user, we're going to generate values for n inside of our for loop. And let's do it like this. So this all would need to be, and I'm going to take this out, make it a little easier to read, I think. So we have the loop here. All right, let's look at what happens. The first thing we do for this particular n, so we're inside the loop. You see where I put the cursor? I'm going to say I'm in the loop. I don't know which step I'm at. Is n equal to 2? Is n equal to 3? Is n equal to 50? I don't know. N is something at this point. I'm right here, okay? I don't know which pass. We could analyze it in that general sense, or we could say, oh, it's the first pass, n is 2. Let's analyze the loop, considering that this is the first pass. Well, let's not. Let's consider this to be some arbitrary pass, or we don't know what n is, but we know it's less than or equal to k. We know it's bigger than or equal to 2. So we start by saying we didn't find a divisor for n. We set that to false. Okay. Now we're going to look for a divisor. When we find a divisor, we'll set this to true. And then when we're done the loop, if we found a divisor for n, well, what am I doing there? I'm incrementing k. Do you see the problem there? It should be incrementing n. That's why I had the infinite loop. K is the value the user enters in. N is the thing that ranges from 2 to k. Okay. And if we found a divisor, then we print n. Otherwise, and then I'm going to print a space, so I don't want the numbers to be smashed together. Otherwise, we print nothing. And then at the very end, just for cleanliness' sake, I'll print a new line. And I'll put a little space there just because we put a space here. Makes it maybe a little easier to see the for loop. You see, I'm being very, very deliberate about my spacing, the line spaces and the indentation. It might look sort of messy and random to you, but it's not. I'm being very deliberate, and And I'm not missing a single space, you know? I don't have like this. Like I'll see student code like that. I'll immediately see that. And that will bother me. And it should bother you. Because even that little tiny bit right there makes it a little harder to read. Oops. So I've got all my spaces there. I'm using 4 spaces here for an indent. And it's consistent. All these indents are exactly 4 spaces. And this here is indented to show that it's a statement that is a substatement of an if statement. This statement here is indented to show that it's a substatement within a for statement. And all of these statements, this one, this one, this one, these are siblings. These are siblings. Sibling children of the outer for loop statement. They all have, all these equal siblings have the same indent. At the same level as this for loop, I have that C out. These are 2 siblings. They are sibling statements at the same level included within the main function. You see how that indentation works? You need to use indents when you write code. Well, for 2 reasons. One is your grade is based on it, and the other is it's very hard to program if you don't do that. So practically every programmer uses indentation to express the relationship between statements and their parent including statements. There are substatements within parent statements. All right, so that's my lecture on that. Is this going to work? Wait a minute. I should have printed 2, 3, and 5. I got something wrong. All right. Well, that's not a hard one to do. If not found divisor for n. Well, let me go slowly on that because that might confuse you. So if we found a divisor for n, we're printing it. But wait a minute. We only want to print it if we didn't find a divisor. We want to print n if that Boolean variable is false. Well, now we got it. This is verbose. It's more than we need, but it might be good for you. You can leave your code just like that if that's more readable to you. So the point is we want it to be readable. But as if you were to do more coding, you might write code that looks like the majority of coders, and there's coders that are old timers that are still doing it like that, it's fine. But this would be more standard. This is a Boolean variable, found divisor for n, and we take its opposite. So if it's false, we'll convert it to true, that exclamation point. That's called a Boolean operator. It's called a logical operator. It works with logical values, values that are true or false. So not false gives true, not true gives false. Let's see that that works correctly. And let's do our test cases, 27. Let's try that. Build that, we modify the code. 27, are we running out of time? We're okay. That looks good. Let's try all of our test cases. I think we did 8. 8 looks good. What else do we have? 2, 3, 4, 8, and 27. 2, 3, 4, 8, and 27. I think it's good. Looks good. Any questions on this one? Did I make it look easy? Yeah. Was it hard when you tried it?
Yes.
It can be very easy, but you just need to practice. It's like playing ping pong. The first time you hit the ball, is it going to go onto the other side of the table? Probably not. Okay, let's. I'm going to use git status, and I can see, like, I don't want to put all this stuff in there, but I'm going to do git add ex2.cpp, git commit lab2 3 rather, exercise 2, right? Yeah, okay. Those comments aren't too important, but in real life situation, that's the comments can be critical. All right, let's copy this code ex2 to ex3.cpp. And we're going to use that for the next problem. Let's see what that is. Factoring numbers. I gotta say, this one I think is the hardest problem. So write a console program that asks the user to enter a positive integer greater than 1. We have that, don't we? Enter an integer greater than 1. That's redundant. I don't have to say positive integer greater than 1, right? That's redundant. If it's greater than 1, it's already positive. So I should remove that. The program computes the prime factors of the number and prints them. For example, if the user enters 100, the program displays 2255. Those are the prime factors of 100. 2 times 2 is 4, times 5 is 20, times 5 again is 100. Develop 8 test cases and verify that your program runs correctly. Include edge cases, such as the numbers 2 and 4. Develop test cases that try to break your program so that you're sure your code is correct.
When you say break your program, how does that happen?
It's a slang for make your program malfunction. Develop a test case, because programs have bugs. Small programs like this don't have bugs, but big programs always have bugs. And so you want to develop a test case that makes the program malfunction so that you discover the bug, you discover the logical flaw in your code. Yeah?
So, like, we can make it malfunction by, like, putting in a number less than 0 or something?
No. Well, if we wanted to do input validation, we're asking the user enter positive integer greater than 1, okay? So the problem doesn't include doing input validation. If I said do input validation and check to make sure that user entered in a number greater than 1, then we would, in that case, test cases would include negative numbers for sure. But we're not doing everything. We're just going to do, we're going to assume that the user enters in a value greater than 1. And we'll develop test cases just to test that situation. Okay? Does that make sense? You want to do the input validation. It bothers you not to do the input validation. That's good.
So,
Yeah. Huh?
what test case would break this program?
Well, I'm going to develop a program that cannot be broken. That's the goal.
Okay.
Well, let's start. Let's write code that has a bug in it. And then we'll develop a test case that breaks that code. And then we'll see how the process works. Okay. All right, so we have one test case already. What did I say? I said that the edge cases, 2, 4, and there's 100. So 100 is 2255, 4 is 22, and 2 is 2. Those are the 2 right there. Here's another one this is a test case that I've used to break student code in the past. 27. And let's do, yeah, 100 is good. Okay. And let's put in, say, maybe 23. That should just be 23. It's a prime. It's a prime number. I'm going to get rid of that code. If we need it, we can put it back in there. Enter an integer greater than 1. So we'll enter in, you know, I like n. So I'm going to do that. And that's it. And let's print, let's just print n. Oh, works. So that test case does not break the program. But that test case breaks the program. It should print 2255. That's what I mean by break. Does that make sense? It doesn't give you the desired results. It's like playing a video game. You know, open a chest and fire a pistol and do something else, and the game crashes. So I know a sequence of actions to take to break this program. Okay. So, all right, let's do it. Now, it takes some sort of contemplation, some dwelling on the problem, and some creative thinking, really, to come up with a solution. And I'm just going to present it to you because I've gone through that process in the past. And I'll show you what I think is the simplest solution. I'm going to use a while loop. And while n is greater than 1, and what we're going to do is pull out prime factors of n. So we'll be reducing n, making n smaller and smaller until it hits 1. When it hits 1, we're done. We can't pull anything out anymore. So let's try some numbers. And let's start with the number 2. So I'll use k as a factor. We're going to start with 2. First we're going to do is pull out as many 2's as we can. So like in 100, we're going to pull out 2 2's. And then once we're done pulling the 2's out, then we're going to try to pull out the 3's. Well, no, so if we take 100 and pull out 1 2, it becomes 50. You can take another 2 out, it becomes 25. Then I can't take any more 2's out. I can't take a 3 out. Can I take a 4 out? I can't take a 4 out because the 2, I already checked the 2's. So if I could take a 4 out, I would have gotten it already by taking out 2 2's. Right? So 4 goes into 100, but it's not going to go into 25 because I already took the 4 out. All right, then, so 4, but we're just going to try 4 anyway because I don't want to put the loop in there to test whether 4 is prime or not. So we're safe to just allow the code to try to divide by 4. That's more efficient than adding the code that checks whether 4 is a prime number or not, and then discarding it if it's not a prime number. So then 5, so we're going to take 2 5's out. After we take 2 5's out, n will be 1, and then we'll be done. So let's do it like this. We'll do if n mod k is 0. So if k divides n, and k is a factor, then what we're going to do if k divides n, now I'll do it like this. Let's print k. And let's take k out of n. And continue with the loop. But what happens if n mod k is not 0? That means k does not divide into n. That means k is not a factor that we can remove out of n. Then we want to increment k. Just had to check for a minute to see if we were in infinite loop, because our loop condition doesn't depend on k at all. So we could just keep incrementing k forever. That's why I paused for a second. I said, wait a minute, I'm incrementing k in a loop, and my loop condition doesn't depend on k. So I had an immediate fear that, oh, I have an infinite loop. But actually, this condition will become false at some point in time. So k won't keep going forever, I believe. Do you see this? See, we want to pull all the factors out of n. This is where, once we find a factor k, that's the point where we pull it out of n. Here, if n is 100 and k is 2, then n becomes 50. Well, what do we do before we turn n into 50? Well, we're going to print the 2, and then we're going to take 100 and divide by 2 to get 50. So we printed 2, and we're left with 50. And we don't do this. This is in the else clause because we entered into here. So we're going to check the loop condition. N is 50. So 50 is bigger than 1. And we're going to try 2 again. We didn't increment k. We left k at 2 because we have multiple instances. But that k may be multiple factors of n. So now we try it again. 50 divided by 2 is 0. I mean, the remainder is 0. So we're going to print the 2 a second time. And then we're going to take 50 and divide by 2 to get 25. So now n is 25. We just printed 2 times, and n is now 25. Well, n is 25, so the loop condition is true. 25 divided by what? Where are we? 25 mod what?
2.
2. And what's that?
H.
What's 25 mod 2? Quick. What's 25 mod 2? 1. Good. Good.
Oh, yeah, for remainder.
So you can pull out 12 2s, that gives 24, and you have 1 left over, right? That's the remainder. So k is n mod k is 1, so this is false. That means we do this. So now k is no longer 2, k becomes 3. N is still 25. It's bigger than 1. We take 25 mod 3, and that's not 0, right? So we're going to increment k, so k becomes 4. And 25 mod 4, well, 4 doesn't go into 25, so that's not 0. So we increment k, k becomes 5. 25 mod 5. What is 25 mod 5? Carefully. I'm not saying 25 divided by 5. What is 25 mod 5? 0. So we're going to print k. We're going to print what? 5. And then 25, n is 25, so we do 25 divided by 5. It gives us 5. N becomes 5. And then we continue with the loop. N is 5, so 5 mod 5 is 0. We print 5 a second time, and then we do 5 equals 5 divided by 5. I mean, n equals 5 divided by 5. So now n becomes 1. That makes the loop condition false, and we're done. Oh, and now I see that we have a bug, because we don't want to print n. Just hit a new line there. Okay.
So we're done with exercise 3.
that code can't.
Not done yet.
So that
Do you
code-
think we're done?
No.
That's good. You have faith, and but we better not program with faith. Okay, that's not going to work. Let's run it. 100, 2255. And what's the other test cases? 2, 3. What was it? 23. Anyway, it looks good, right? Maybe that number's too big. Hey, something's wrong. I think it's too big. It maybe exceed the size of an integer. Look at that. That was fast. You know, it shouldn't stop with a 1, 2, 3, 1, 2, 3, 1. Think that's prime? That's prime. Okay. Do you believe that that's prime number? Do you have enough faith in what we coded, the test cases? Would you make a bet on this? Would you bet $100 that was prime? All right. Let's do exercise 4. Oh, wait. We need to add. We need to get commit.
I'll say the fourth one was fine. The fourth one, he said it didn't work. So I'll just do the fourth one.
All right, exercise 4. We're almost there. 15 minutes to do this.
How many exercises are there?
That's it. That's the last one. Generating random colors. Write a program that generates a different list of 100 random RGB color values using hexadecimal notation. A program should write something like the following. Does everyone know color values? I'm going to show you a quick example. You know, look in this is the browser, like the developer interface, developer tools. And you can examine these colors. See the color value there? DC, DC, DC right there. That's the background color. See that? That's the background color of the body element. See there's a gray in the background here? That color is DC, DC, DC. So that's red, green, blue. The red is DC, the blue is, so that's why it's gray, because there's an equal amount of red, green, and blue. Just to show you, that's where these numbers come from. Those are the 6 colors are represented by 6 hexadecimal digits. Well, there's other representations, by the way, but this is one. Okay, this is it's kind of a standard common representation of color values for displaying colors on monitors. All right, so we want to generate 100 random color values. That's a lot, yeah. So let's do this. So we need strings that are composed of these characters. We need to randomly select from this and add it to the string. Let's do that. Well, I can't remember how to do this, but we'll figure it out. We got 15 minutes to do this. No test cases on this one. It's easy to see. All right, let's do this. So let's think about, it's all, what are we going to do, right? I mean, it's like feel like crisis. I don't know what to do. Is that how you feel? So we have this sort of fuzzy cloud. We have no concept at all. Well, wait a minute. We have to print 100 things. We got to do something 100 times. What does that make you think about? That's a loop. It runs exactly 100 times. So we're going to do something 100 times. And we're going to print, you know, that's the one we looked at, right? Let's do this. Let's print that. That's a color value we saw in the browser. I hope you see what I'm doing here. EX4. What did I do wrong? Forgot the semicolon.
Hey, yours says it, but when ours is like, it's weird.
What?
Yours says it clearly when you say something.
Mine is easier to read. That's because I'm the instructor. So we give you the harder ones to figure out. Just kidding. Yeah, maybe that is because of the color, you mean, that thing? Makes it easier, yeah. I don't know why. I don't know how that came up red. I don't get it. So my terminal must be smart. I don't know what's going on there. Let's run that. Okay, that looks good. I mean, we could see if it's 100, we redirect that into T, and then we'll open up T, see that? And if I jump to line 100, and this is the end here, right? So this should be the 100th number. So if I jump, watch this, I'm going to jump to 100. That's it, right? So I got exactly 100. I don't know if you wanted to do that. That's a way to verify that. All right, now we need this. We want this string to be random. That means we need something. We need the source of randomness. So we're going to call this rand function, and let's get a number from the rand function. We're going to get, say, m. Now that gives us a number between 0 and the largest possible integer. And we only want 16. We want to pick from a set of 16 different characters. See this set here, there are 16 digits in the hexadecimal number representation system. So I'm going to do mod 16. That gives me, n is going to be either 0 or 1, all the way up to 15. And then let's do this. So let's do it like this. Let's keep it simple. Let's just print n. Let's see what happens. So, it's hard to deal with 100, so I'm going to break it. I'm going to set it at 10. And then we'll bump it up to 100 when we're done. What happened? I didn't compile. There it is. Oh, so you can see these are random digits from 0 to 15. Oh, but look, we get exactly the same sequence. What's wrong? I want a different sequence each time I run the program. What's wrong with the code? What do I need to add? I need to do what? I need to do what? See, it's like generating your Minecraft world, which is a random generation algorithm, but you're using the same seed all the time. You can do that. You can set the same seed and get the same world. Huh?
Where did you put the seconds?
So you need to seed the random number generator. Now watch this. When I run it, I'll get a different sequence. See that? Because the seed is different. I set the seed to 3. Oh, but the seed is always 3 now. So I get a different sequence, but it still remains the same. So we want to get some variation in there. So just a little trick here. Sorry. We're going to enter in the number of seconds since 1970. That's what time 0 gives. It's a current number of seconds from some epoch, typically 1970. Let's see, that may not compile without an include, by the way. It does in my system, but I think, let's check this. The sequence starts with 4, then it goes to 6. Oh, now it starts at 14. So there we go. We have randomness now. You might need to include, was it C standard live?
How is yours working?
Is that it?
I don't know.
Is that what you need to do?
It's in the first line.
In the lab, does anyone remember? Well, it doesn't break it, right? I can't put anything in there. Right? I can't just put anything in there. So that really is a header file. And I believe that you might need to include that in the labs to give you time.
How does yours
But see, that's compiler dependence. In my compiler, I get the declaration for time already without having to include that. Okay, we're running out of time. Let's do this. This is not, it seemed like a hard problem, right? But when we break it down into little steps and add one piece at a time, it becomes a simple problem. And this is simpler than the last problem. The last problem about the prime factors, in my opinion, is a harder problem than this one. So we're printing these random numbers, but we need to do something different. There's many ways of doing this. I'm going to show you one way. So if n is less than 10, then let's just print the n. And I don't want this. No, I'll leave that in there. Sorry. For now, I'm going to leave it in there. But if n is greater than 10, I'm going to use an else if. Else if n equals 10, and like that's an extra space, I want to keep all my spacing the same. You know what? I want to get rid of this. I got to get rid of this. A, because 10 is, decimal 10 is hexadecimal A.
Would you put a single parenthesis? Or I mean a single quotation?
And 11 is hexadecimal B. And 12 is C. And 13 is D. And let me see, and then there's E and F, right? So I need 2 more. Did I do something wrong? 10, 11, 12, 13, 14. Did I just mess that up? Replaced by 4. That's D, E, F, and this is 15, right? How about this? What should we print here? Should never reach there, right? Did I spell wrong, right? That's right, there's no E.
That's right.
I'm a really bad speller. Okay. You know what? That's a trauma. When I was a TA a long time ago, I spelled wrong with an E in a class. Everybody laughed at me. I still have that trauma, like 30 years later. Okay. I think that's going, and then after here, then what I'll do is I'm just going to print a new line here. That looks good. Look at that. Look at that. Oh, but we need 6, right? How are we going to do that? How are we going to get 6 on a line?
Make a loop underneath the first loop.
We're going to use a nested loop. Right? So this is the outer one. This gives us the 100 numbers, or 10 right now. And then we'll have an inner loop here, and we'll use J. And J will just go from 0 to 5.
Oh yeah, you can do 1 to 6.
See that? There's probably a better way to do this, but I'm doing it this way. Whoops. I don't want it in there. So I generate that digit and print it 6 times before I print the new line. See that? So I'm using a nested loop there. Does that look good? Now the final thing is set it to 100. Need to compile. There it goes. We could check to see if that's 100. I'm going to add it to the repository. That's it.
So can you go back to the